Hey, and welcome to my video on the half-life for a first-order reaction. So we're going to give this the symbol T sub half, and remember a first-order reaction. So you've got a reaction A goes to P, and what makes it first-order is that you've got a rate law that looks like K times A to the 1. And we saw in the last video, right, or actually I guess a few videos ago, that there is an integrated rate law. So that tells us how the concentration will vary with time, and it looks something like the log of the concentration at time T is minus K times by the time plus the log of the original concentration. And there's also a second way we can write this. So we can actually also write it as the log of the concentration at time T over the original concentration is equal to minus KT. We'll probably see that's the most useful way to look at this. So we've got a half-life situation going on here. So in order to mathematically calculate this, we're going to say, look, at time 0, the original concentration, right, we're just going to call A sub 0, right? That seems pretty good. But at a time given by the half-life, right, we're trying to solve for this, then the concentration at that time T is equal to 1/2 of the original concentration, right? So that's what makes it a half-life. It's the time it takes for half the concentration to disappear. All right, now we plug it into the equation. We plug it into the bottom integrated rate law. So we got the natural log of the concentration at time T. All right, well, at the half-life, right, that is 1/2 the original concentration divided by the original concentration. Alrighty, and that's equal to minus K times the time, and the time we're looking at, right, is the half-life. We can simplify this a little bit, so we can see that these will cancel out, and that now gives us the log of 1/2 is equal to minus K times by the half-life. What do we want? We want the half-life. When do we want it? Well, now, actually. So that's equal to the log of 1/2 over minus K. And you can go ahead and do a little bit of math here. The log of 1/2 is minus 0.693. So over minus K becomes positive 0.693 over K. And if you're wondering where's that 0.693 come from, it's actually equal to the logarithm of 2. So it's not a magic number, it's just the logarithm of 2. So what is that telling us? That is telling us something that is pretty nifty. And as opposed to a zero-order reaction where the half-life keeps getting shorter and shorter, we can see that this is a constant. The rate constant, right, is a constant for a reaction at a particular temperature. So it takes the exact same amount of time for half of the reaction to be used up. And even when half the reaction is used up, it still takes the exact same amount of time for the next half to be used up. So let's go ahead and graph that and look at what that is telling us. Okay, so imagine we've got a rate constant for a first-order reaction, and the rate constant K is equal to 3.8 times 10 to the minus 3 per second. And we can calculate the half-life for it. It's actually just the log of 2, so 0.693 over K. And when we do that, we get 182 seconds, right? Or actually, I guess with significant figures, 180 seconds. Which is, let's see if I can do the math right, 3 minutes. So that means every 3 minutes, half the reaction is used up. So now if I go ahead and I plot the concentration of, let's call it A versus time, every 3 minutes, right, it's going to be half of the original value. So if we look at percentages, right, so that makes it a lot easier. 100% is going down to 50%. And the amount of time it's taken is 3 minutes. So I can go ahead and I can put 3 here. I'm going to make this the time in minutes. And as we go down another half, so half of 50% would be 25%, it's going to take another 3 minutes, so 6 minutes. As we go down to half of 25%, that's 12.5%, or 1/8. 1/8, that is going to be another 3 minutes. And as we go down to half of that, that is what, 6.25%. That is going to be another 3 minutes. So we've got something that looks like this. And I'm going to go ahead and try and plot this. And I'm pretty lazy at drawing, so bear with me. So it is looking like it's getting closer and closer and closer to zero concentration, but it never quite gets there. It always takes 3 minutes to get half of the way there. So this is actually, if you're a math person, right, this is actually an exponential decay. So you got an exponential decay curve here, and essentially every 3 minutes, right, half of it goes away. It never really quite goes away, but sometimes people say after 8 or 10 of these half-lives, it's pretty much gone to zero. I mean, there's a few molecules left after 8 or 10 half-lives, but essentially 99.99999% of it's gone. So there you go. So I suppose before we move on to a second order half-life, the most important thing I suppose to get out of all of this at the end of this is that the half-life is a constant only for a first order reaction. So anytime you got a first order reaction, the half-life itself is completely unchanging. In fact, for nuclear decay, right, for any kind of radioactive decay, they're all first order reactions. They're not chemical reactions, they're nuclear reactions, but still the same thing. It's a constant amount of time for half the material to decay away. So that's actually a way you can tell if something's first order, right? If it takes the same amount of time for half of it to go, bingo, it's got to be a first order reaction. All right, let's move on to second order.